Let's start by discussing integration of vectors. So you can define the integral of a vector, and notice that these are bold letters, which means that they are vectors. If I was handwriting, I would do the arrow. Yes? So the integral of a vector with respect to its variable, so notice that the vector is a function. In this case I chose t, it could have been x, but it's a single variable. Yeah. So this is a vector that depends on a variable, and I'm doing the integral with respect to that variable. And the result is a vector. That is really important. So how do you calculate this? So the way you can do it is I is equal to the integral from a to b of the vector. And the vector, you can expand it in a certain basis. Okay, so in general, any vector v can be written as v1 times e1 hat plus v2 times e2 hat plus dot 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 vn times en hat dt. And now you can apply the linearity of the integration. Which means that the integral of a linear combination is equal to the linear combination of the integrals. Okay? This is true as long as assuming that the basis vectors e1 hat, e2 hat up to en hat are constant. Or in other words, they are not a function of t. And I will have later a video explaining what to do if the basis vectors are a function of t. But if they are constant, then it's very easy. You can just apply linearity and take them outside of the integral, so that the result is equal to the integral from a to b of v1 dt times e1 hat plus the integral from a to b of v2 dt times e2 hat plus dot 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 the integral of a to b of vn dt times en hat. Okay, so that's how you calculate the integral of a vector. If you want to write it differently, maybe you would like to write vector v, instead of writing it as a linear combination of unit vectors, you want to write it as a column. Yeah, so you have your vector v, which is equal to v1 v2 up to vn, and this is in the basis e1 e2 en. Yeah, and now we do the integral. So the integral of this vector with respect to t, and the result is another vector in which each component is the integral of the component with respect to t. The second component is the integral of the second component with respect to t. And the nth component is the integral of the nth component of the vector with respect to t. And that's it. Okay, so this and this are saying the same thing, just writing it as a linear combination of the basis vectors, or writing it as a vector. Okay, so this will be our result, I vector. Excellent. What is the physical meaning of integrating a vector? I recommend you abandon the idea of integrals being the area, because then it becomes almost impossible to understand, because here we have a vector, so the area under what exactly? It's very tricky, right? It's much better to think of the integral as an addition of little elements. Okay, so the same way that the normal integral of one-dimensional functions, so f of x and x, if you do the integral between a and b of some function f of x, yeah, so one interpretation of the integral is that you are adding little rectangles of a width that is infinitely small, a width dx, and you are adding the area of those rectangles, right? You remember that. So that was in one dimension. Actually, let me move this away and here. So this was in one dimension. So when the output is a single dimension. So now when we have a vector, what is going on? The best way I can explain it is with an example. So an equation you have used in classical mechanics is that the total position moved by an object is equal to the integral of the velocity with respect to time. So you were already doing this integration of vectors. So what is this integral saying? So this is basically looking at an object that is moving through a path in space, yeah? Yeah. And you want to find the total displacement r, which is this displacement here. But this displacement here is just the addition of all of the infinite displacements. So you have to add the displacement here, plus the displacement here, plus the displacement here. Okay, so you add all of these little arrows. So each of these little arrow is a vector, which means that when you are adding vectors, you have to put the tail of one vector on the head of the other, and you have to add them that way, right? So the addition of all these vectors is equal to the vector r. But what is each of these arrows? So each of these arrows is how has the object moved in a very small time. So let's call that small time dt. Okay. So when time changes by an amount dt, the distance traveled by the object is equal to the velocity at that time t multiplied by dt, right? And that is this small arrow here. In the limit when dt goes to 0, similarly to what we did in one-dimensional integrals, we do the limit when dx goes to 0, so we end up finding the area. So here we are making the limit when dt goes to 0, so we have like an infinite amount of infinitesimal arrows that are all adding up to the final arrow r. And that is why the position vector is equal to the integral of d of t with respect to t. Okay? So that is the meaning of integrating a vector.